So we're going to go over the solutions for the G2 reflection. This lesson focused on sampling distributions for proportion. So that'd be about the first 5 problems. Plus we'll do a little bit on transforming for linearity, normal distributions, and probabilities. So you should have some nice practice of the current and the old information. Problem 1, which of the following is a true statement? The sampling distribution of p hat has a mean equal to the proportion p. So I pulled this straight off the math formula chart, and you can see the mean for p hat is actually p. So that seems to be true. Let's look at statement B. The sampling distribution of p hat has a standard deviation equal to np times 1 minus p. Well, actually, the standard deviation for p hat is p times 1 minus p over n. Take the square root of that. This other one, that's from the binomial distribution for x, the number of successes. So B is incorrect. Then C says the sampling distribution of p hat has a standard deviation that becomes larger as the sample size becomes larger. Well, if you look at the formula right here, you see this n? Well, basically the bigger that is, the smaller the number will be. So that means that our standard deviation will become smaller as the sample size increases. So that is incorrect. The sampling distribution of p hat is considered close to normal provided that n is greater than or equal to 30. So in your packet, I have this nice set of notes that includes the conditions for the distributions. And you can see for proportions, the normal condition is that np, the number of successes, is at least 10. And n times 1 minus p is at least 10. We often call this the large counts condition. So D is incorrect. And because we have to meet this condition, we know that it's not always close to normal. So E is incorrect, and that leaves us with the answer of A. Number 2, which of the following conditions do not need to be met when using a normal distribution for the sampling distribution for proportions? Well, we're going to conditions to check. Again, this is straight out of that math chart, or that chart that I gave you in your packet. And you can see here are the conditions. Simple random sample. The normal condition, also known as the large counts condition for np greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. np is the expected number of successes, and this is the expected number of failures. So A and B are true. And then you can see for standard deviation calculations, we need to meet the 10% rule that our sample size is not more than 10% of the population, or you could say the population is at least 10 times the sample size. And then finally, the only condition not listed is n is at least 30. This is for sample means, not proportions, which you'll learn in the next lesson. Number 3, researchers found that in the aftermath of the 2011 Fukushima nuclear disaster, 12% of the pale grass butterfly larvae developed mutations as adults. What is the probability that in a random sample of 300 of these butterfly larvae, more than 15% develop mutations as adults? So the cool thing here is they have a z-score. Z-scores are true for any distribution. And we're going to go ahead and do our calculation. By the way, I could check conditions on this. We have 300 butterfly. For sure, that's not more than 10%. And if I did the 12% of 300, that would be 36. That's at least 10. And the 88% is also at least 10. So don't worry, we're going to practice conditions on 4 and 5. So here we go. We want to know what is the probability that Z is greater than a certain value. So we're going to do value minus mean over standard deviation. The value is 0.15 right there. And the mean is 0.12 because they told us that was the mean. And then we can calculate the standard deviation. So it's going to be, don't use the value here. Use the mean, all right? So you got to use 0.12 in there. So once you do that and substitute, you find that the answer is P. 34% of Americans say that math is the most important subject in school. In a random sample of 400 Americans, what is the probability that between 30% and 35% will say that math is the most important subject? Should be more. Anyways, so let's write down what we know. The true proportion is 0.34. We have a sample of 400 Americans, and we want to know the probability that the proportion is between 0.3 and 0.35. So first of all, get in the habit. This is where people implode on this unit. This is where it gets hard, where it gets real. And where does it get real? Checking conditions. This will be worth half free response work at least. So, because there's a couple things you got to do. So looking at your table, you have the simple random sample condition. Well, they said in a random sample, 400 Americans. So let me go ahead and highlight that. So they said it is a random sample. Look at that, in a random sample. It says it in the problem. Okay, so we have our random sample. Large counts. We've got to check n times p and n times 1 minus p. You need to show the calculation. This step, all this math, should be shown. All right, you don't show the math, you haven't shown the condition. Successes and failures here, we got 136 and 264. Those are both at least 10, and your condition has been met. 10% rule. 400 is less than 10% of Americans. So there are a couple ways you can go through this. You can say the sample size is less than 10% of the population, or you can say it's reasonable to assume we know there are more than 4,000 Americans. So you notice where I got the 4,000. How did I get that? You take your sample size and multiply it by 10. If you're pretty sure your population should be bigger than that, then you can say it's reasonable to assume that the population is at least 10 times the sample size, and your condition is met. So we met all conditions. We met all conditions. We can use the normal distribution. So now we're going to get to the mathy part. Again, this whole piece here is like half of the points on problems. You must show that you're allowed to use the normal condition before you start using the normal distribution. All right. So when we're using normal distribution, we need a mean and we need a standard deviation. Well, we already know our mean is 0.34. So that's up here. See that right there? So I don't have to go calculate that. Now I need to go find my standard deviation for proportion, which is right there on the math chart. And I'm going to substitute this p and that n right there into the formula. So you can see it there. Calculate it. You get a big, giant number on your calculator. Now, the biggest issue I see here, some people are like, oh, it's 0.02. Not good enough, guys. Include a couple digits, all right? So I personally, there are 3 sig figs right there. I like to have 3 sig figs on my standard deviation. You can have you could probably get away with 2, at least to the thousands place, in my opinion, all right? I personally like 3 sig figs. So if I were putting this in Staplet, there's my mean, there's my standard deviation, and then I say from 0.3 to 0.5, so you can see there's a 0.3, there's a 0.35, there's the area, 0.6177, which does give you 0.618. But being a good teacher, I also need to practice showing you how to do this with the calculator, so here we go. Okay, and just to remind you how to do this on the calculator, because you will need to be able to do this on your own. Second distribution, normal CDF, because we're doing an area. This one does values. Number 3 does values. So like on your drop downs on the Staplet, this is the top one for finding percentages or probabilities. Number 3 is the second one for finding values if you know percentages or probabilities. So I'll hit enter. We can go there. And we said we're going between 0.3 and 0.35. And we're putting in our mean of 0.34 and our standard deviation of 0.0237. And voila, matches the answer we have on the Staplet, 0.6177, which rounds to 0.618. All right, number 5, binge drinking is a serious problem killing more than 1,700 college students per year. Be careful, guys. Suppose that the incidence of binge drinking is 43% and 37%, respectively, at 2 large universities. So that's the thing to keep in mind. They do say these universities are large. That will be important later. In a random sample of 75 students at the first school and 80 students at the second, what is the probability that the difference, first minus second, between the percentages of binge drinkers is between 5% and 10%? So first of all, let's write down all the values we know. There's a proportion 0.43 from 43%. Our sample is 75 for the first university. And then for the second one, it's 0.37 and a sample size of 80. And we're curious of between 5 and 10%, which would be 0.05 and 0.10. So we need to check conditions for normal, all right? So simple random sample, given a random sample of 75 students at the first school and 80 at the second. See right here? It says random sample. So that condition is met. So you just need to tell me that, okay, don't just say given and then done. Include some words and say the condition is met. You can copy it out of the thing. In fact, that's pretty much what I did. I just copied the words out of there and said, yes, it's given that a random sample of 75 students at the first school and 80 students at the second. So we're good there. Large counts condition. You have to check both of them separately. And it may seem annoying. I know, because you got to multiply two numbers 4 times. Yes, you do. You need to show me this calculation, all right? So for N1, P1, N1, 1 minus P1, N2, P2, N2 times 1 minus P2. Now you can see that all of these are greater than 10, so this condition is met. By the way, there's a nice thing. You can always double check your math. 32.25 plus 42.75, yeah, that should be about 75. 29.6 plus 50.4, that is 80. So your number of successes and the number of failures should add up to your sample size for both. Finally, the 10% rule. It is reasonable to assume that there are at least, so in this situation, instead of me saying 75 is less than 10% of the population, what I did is I multiplied the 10 and the 75, got 750, and then the 10 and the 80, and I got 800. I said it's reasonable to assume there are at least this many at each large university. Remember, they said it was large, so you should have more than 750 students. You should have more than 800 students. So we can use the normal distribution. So now we'll get on to the calculations. So I need a mean, and my mean difference, well, I'll just be subtracting those two. Let's go ahead and calculate the standard deviation, which can be a bit of a bear. Yes, this is not my favorite equation to use, P1 times 1 minus P1 plus P2 times 1 minus P2. You might need to be careful how you put parentheses on there. Sometimes I'll do this in the calculator just to be safe, all right? So once you substitute that all in, you should get a standard deviation of 0.0786. And our mean difference is just the difference in the two proportions, or 0.06. So when I put 0.06 and 0.0786 in my stapplet and look for between 0.05, see there's my 0.05. Don't worry that it says X, that's what stapplet does. Then it gives me an area of 0.2452, which is that answer right there. But I still should show you how to use the calculator because I'm going to block the normal distribution on the stapplet. You need to start learning how to use it. So since we have a single standard deviation for the difference and a single mean for the differences, it's pretty much the same steps as before. We're trying to find area, so we're using number 2, the normal CDF. Our lower in this case is 0.1. And then that's not the lower, that's the upper. Always. By the way, you might put these in the wrong order and it can give you a negative, so we'll do that. Just an FYI. So if you ever get a negative value, that's what's going on. The mean difference between the two proportions is 0.06, and our standard deviation is 0.0786. Hit enter. And it matches our answer from stapplet, 0.245. Number 6, the Venn diagram below, or to the right really, describes a proportion of students who take chemistry and Spanish at Jefferson High School, where A, and that would be the, let me go ahead and this. So A really refers to this circle right here, all right? And then B refers to this other circle that's overlapping right there. So A is a student who takes chemistry, B is a student who takes Spanish. Suppose a student is chosen at random. What is the probability the student doesn't take Spanish or chemistry, all right? So we're looking for this area out here that's outside of the Spanish and the chemistry. Well, all probabilities must add up to 1. So I know that if I add up the probability of not chemistry and not Spanish, plus 0.2 plus 0.1 plus 0.3, I need to get 1. Combine these, we get 0.6. And so the answer is 0.4. So this one's actually pretty straightforward. Number 7. The manager of a water park collects data on daily high temperature and the number of customers entering the park for 15 summer weekdays. Based on these data, he produces a least squares regression equation to predict y equals the number of customers based on x equals daily high temperature. The equation is y hat, or predicted y, equals negative 3110 plus 51.2x. On one day, the high temperature was 93 degrees Fahrenheit and 1,700 customers entered the park. Which of the following is the residual for this observation? So first of all, I'm going to go ahead and get the data point. So it's 93 degrees Fahrenheit and 1,700 customers. And the question is, what is the residual? I do not like x and y when I'm working on this. I'm going to replace those with words. So I'm going to say predicted number of customers equals negative 3110 plus 51.2 times the daily high temp. Then I'll go ahead and substitute 93 in here. And my predicted is 1,651.6. Well, the residual is actual minus predicted, so I'm going to substitute in the 1,700, which was the actual, and 1,651.6, which is the predicted, and I get 48.4. By the way, you might be asked, oh, did you over or under predict? Well, it's so much easier just to compare the predicted to the actual, and you can see we under-predicted. Some people say, oh, if the residual is positive, you under-predicted. I don't do that. I just compare actual and predicted because it's way easier to figure that out instead of memorizing a new rule. We got enough to memorize. We don't need more. All right, suppose x is a continuous random variable taking values between 0 and 2 and having the distribution shown at right. What is the probability that x is greater than 1.5? So this is a probability distribution function. It's not a normal distribution. It's a weird distribution, a triangular distribution. So the probability that it's greater than 1.5 is in this area. All right, so we'll go ahead and mark it and shade it. And then this is just the area of a tiny triangle, which is 1/2 base times height. The base, well, this is at 1.5, so the base is 0.5. And this is only a quarter of the triangle, so it's only a quarter of the height. So it's 0.25. A quarter of 1 is 0.25. When I substitute those two values in and multiply, I get 0.0625. So the probability of being over here is about 6.25%. Number 9. During the years 1886 through 2000, there were an average of 8.7 tropical cyclones per year, of which an average of 5.1 became hurricanes. Assuming that the probability of any cyclone becoming a hurricane is independent of what happens to any other cyclone, if there are 5 cyclones in 1 year, what is the probability that at least 3 become hurricanes? So I'm pretty sure this is a binomial distribution because we have a probability that a cyclone becomes a hurricane. So we're going to check Binge for a binomial distribution. Binary, 2 outcomes. Yes, either it becomes a hurricane or it doesn't become a hurricane. Independent. The problem states, if you look right here, it says the probability of any cyclone becoming a hurricane is independent. All right. And then N is the fixed number of trials. So we're going to try 5 cyclones. So there you go, 5. And same, the probability is the same, so we're going to use a proportion. So now we'll get to calculating. So the proportion of cyclones that become hurricanes is, on average, 5.1 out of the average of 8.7, or 0.586. We know we have 5 trials, and we want the probability that 3 or more become hurricanes, at least 3. So if I did this on Scatterplot, it kind of looks like this. Now, I could get the answer from Scatterplot, but that's not the goal. I want you to visualize this because the possible number of hurricanes is anywhere from 0 to 5. And you can see here we expect very close to an average of 3 hurricanes, maybe, might be slightly more, might be slightly less. All I'd have to do is multiply 5 times 0.586. It'll be slightly less. And the question is, how big is this area? Which I could do directly if I'm using Scatterplot. But if I don't let you use, I still will this test. So I will on test G, I'll still let you use the binomial Scatterplot because it's a more recent unit than your normal distribution unit. But you should start getting ready to do this on a calculator. So Scatterplot, I can do this directly and figure out the number. On the calculator, it does not do right-handed areas. It only does left-handed areas. So I have to say, oh, if I want this area, I have to subtract this area, which is the probability that x is less than or equal to 2. All right, so that's basically going to be a binom CDF of n equals 5, p equals 0.586, and x equals 2. So to get to binom CDF, we hit second, distribution, and it's always at the bottom. So there it is, choice B, hit enter. PDF will do for an exact value, like x is exactly 2, but we want from 0 to 2, so we're doing CDF. And remember, it only does left-handed, so it always starts at 0. We have 5 trials. Our P is 0.586. And then our x value is 2, and enter, and then you get 0.342, but that's not our answer. We want to subtract that from 1. 0.658. So there we go. 1 minus 0.342 is 0.658, which is your answer, D. Number 10. Given the probabilities P of A is 0.3 and P of B is 0.2, what is the probability of the union, probability of A or B, if A and B are mutually exclusive? What if they're independent? What if B is a subset of A? So these are 3 different problems, which is probably why most of these have 3 different answers. So let's start off first with A and B being mutually exclusive. So if A and B are mutually exclusive, then the probability of A and B equals 0. All right, so let's go ahead and make a note of that. This formula is directly on your math chart, front page in the probability section. It's right there. All right, so we're going to go ahead and substitute in the 0.3, the 0.2, and 0. And we get 0.5. All right, so we're pretty sure it's either C or D. Now let's go ahead and then do independent. Well, if A and B are independent, then the probability of A and B is just the probability of A times the probability of B. Now, some of you are probably going, Mrs. Overman, if it's 0.5 on the first one, we know this one's 0.44. Yes, you do. But let me go ahead and make sure you know how to calculate it. All right, so we know I can just substitute in 0.3 and 0.2, multiply them out. I get 0.06. So using the same formula, but now we have a different number for probability of A and B. Now it's 0.06 instead of 0. So we substitute that in, and yes, we did get 0.44. So now we have a very interesting one. What if B is a subset of A? So what does that mean? All of B falls in A, and we know the probability of B is 0.2. So if B is a subset of A, then the probability of A and B happening at the same time, that only occurs here. So probability of A and B is just 0.2. So we write the formula down again, substitute, and now we get an answer of 0.3. So our answer is D. Number 11. A medical research team tests for tumor reduction in a sample using 3 different dosages of an experimental drug, cancer drug. Which of the following is true? So we're looking at number of explanatory variables and response variables, I guess. Usually we're very interested in the explanatory, all right? So first of all, What is our explanatory variable? Well, it's 3 different dosages of an experimental cancer drug. So it could be it's 0, 1, or 2, or it could be that everybody's getting it. Not sure, but there are 3 dosages. I have the feeling one of them is 0, by the way. So there are 3 levels of a single explanatory variable. It's only the experimental cancer drug that is explaining the tumor reduction. All right, so tumor reduction is a response variable. Number 12. Mr. B's statistics class had a standard deviation of 11.2 on a standardized test, while Mr. M's class had a standard deviation of 5.6 on the same test. Which of the following is the most reasonable conclusion concerning the class's performance on this test? Standard deviation is a measure of variability. Mr. B's class has a higher standard deviation, so more variability. Homogeneity is the opposite of variability. So we can say Mr. M's class, which doesn't have so much variability, is more homogeneous than Mr. B's class. On to number 13. The appraised values of houses in a city have a mean of 125,000 with a standard deviation of 23,000. Because of a new teacher's contract, the school district needs an extra 10% in funds compared to the previous years. To raise this additional money, the city instructs the assessment office to raise all appraised house values by $5,000. What will be the new standard deviation of the appraised values in the city? Well, honestly, when I first read this, like, oh, we're raising values by 10%, needs an extra 10%. Maybe I need to multiply this standard deviation by 1.1. But they didn't do that. What they did is they raised all appraised house values by a constant. Since each data point is shifted by 5,000, the data is shifted, but the spread doesn't change. So if you want to get all equation-y, standard deviation for our new, let's see, whatever it is, the taxes or appraised values. So the standard deviation for our new appraised values is our old value plus 5,000, right? But when we add a constant, we know we can ignore it. And so the standard deviation is exactly the same. It is $23,000. Number 14. A talk show host recently reported that in response to his on-air question, 82% of more than 2,500 email messages received through his publicized address support the death penalty for anyone convicted of selling drugs to children. What does this show? So first of all, he does not send the survey to the recipient. Survey respondents have to volunteer and go and click on the link. Oh, bad data. Very, very bad data. This survey is meaningless because of voluntary response bias. Do not just post up a link and think your data is fantastic. All right. Number 15. You have data for many years on the average price of a barrel of oil and the average retail price of a gallon of unleaded regular gasoline. If you want to see how well the price of oil predicts the price of gas, then you should make a scatterplot with blank as the explanatory variable. Well, if the price of oil predicts the price of gas, then that is the explanatory variable, the price of oil. Number 16. A scatterplot of y versus x shows a positive nonlinear association. 2 different transformations are attempted to try to linearize the association, using the logarithm of the y values and using the square root of the y values. 2 least square regression lines are calculated, one that uses x to predict log y and the other one that uses x to predict square root of y. Which of the following would be the best reason to prefer the least squares regression line that uses x to predict log y instead of square root of y? Well, we transform for linearity when we see patterns in the residuals, all right? The linear transformation is appropriate when the residual plot shows no pattern. In other words, the more random the scatter, the better. And that's the end of this assignment.